Yeah. So yeah, hi everyone, and welcome to the 13th chapter. We had quite a few weeks break, but because of the daylight savings. So this is we're resuming the chapter discussion on the book discussion on the Gen AI. We had a chance to cover the first 12 chapters already. From chapter 1. I think the first 3 chapters were covered by Derek, and then Diana took the first 6 chapters, and then Diana took the next 3. And I don't know if Daniel is here, but Daniel took the next set of 3 chapters. So today we are supposed to cover the section 3 on foundations for modern language modeling. Which we're going to cover today. We're essentially going to cover the chapter on tokenization, and then we're going to sort of briefly review positional encoding. But these concepts build on some of the themes or the key themes that were initially shared in prior chapters. Some of the foundational and preliminary content that was shared by Derek and Dan and David earlier on. So I'm going to cover mostly tokenization and then positional encoding as we go through the material. And the main goal of the chapter here is to understand the main foundational concepts for training modern large language models. So that would be our focus. So what is tokenization? Tokenization is really at the heart of all the I would describe this as some of the difficulties, the weirdness that we see with large language models in general. This is a screenshot from some material from Andrej Karpathy, who has really put out a lot of resources out there. You should visit his YouTube channel. He's put out a lot of resources out there teaching about how large language foundationally work. And one of his quotes there was, tokenization is at the heart of much of the world weirdness that we see in large language models. That why can't large language models spell words correctly? The answer is tokenization. Why can't large language model do simple string processing tasks? The answer there is tokenization. Why can't large language models, why is LLM worse at non-English languages? The answer is tokenization. Why is LLM bad at simple arithmetic? It's essentially tokenization. Why does LLM fail us? So all the weirdness, whether it's hallucinations and the different difficulties that we see with large language models are pretty much tokenization is pretty much at the center of all those hallucinations and all those challenges. So it's pretty foundational to how large language models work. So that's why we are doing this. But like I said earlier, this lesson here is going to build on some of the foundational lessons that we had earlier. I think we covered quite a few things in the first in the earlier part of this course. So I think at the beginning we had Derek walked us through the first initially, I think the first class we had the first 3 chapters, and we covered the AI landscape, essentially where we are in terms of AI development. I think many of you are aware that we are witnessing a huge explosion in the development and deployment of large language models. We know about OpenAI's ChatGPT, we know about Gemini, we know about X's Grok, we know about Claude AI from Anthropic, we know about Meta. So they've just been, Mistral from I believe from a group in France. So there's been a massive explosion in the deployment of different large language models, and more conversations on multimodal integration. So shifting from not only text-based information or text-based token, but also the integration of imaging and video generative AI capabilities. So and we've kind of seen a growing in that field as well. And I think as the AI landscape is continuing to evolve in 2025, there's been increasing conversations around AI safety, alignments, and conversations around the potential economic disruptions that is causing. I've heard a lot of debates around open and closed language models and all that. So I think Derek really did a really great job, laying that foundation. Then we talked about the content landscape, because it's things are changing so fast that it's so difficult to stay up to date with information. You can write a textbook today on on AI, on some part of it, and it can quickly become outdated very quickly. So there's not really like a singular resource that has all the information. Even the book that we are currently using probably would need to be updated frequently as information. So the information on learning generative AI is pretty much scattered all over the internet. You'll find this in blog posts. A lot of people are making videos and posting on YouTube. I've seen a lot of discussions on social media platforms like Twitter or LinkedIn, Blue Sky, etc., etc. So a lot of online discussion. So the information on generative AI is pretty much is getting scattered, and it's increasing at an exponential rate. So definitely need to have a resource that sort of consolidates some of that material somehow for us. Some of the preliminaries that we talked about for this book club was there's the importance of mathematics, essentially calculus and linear algebra. And I think in the textbook there is a video there on if you need to refresh, if anyone who is watching needs a refresh, there's a video here on the essence of calculus and linear algebra and how that connects to generative AI. So really encourage you, those who don't have foundation in mathematics, in arithmetic or mathematics, to go back and look into those as well. Programming as well is important. Python in particular is kind of lays at least basic um knowledge on Python is very foundational as well. But there are also others. I think C++ is becoming increasingly popular, and there's CUDA as well. CUDA is not a programming language. I think I mean I've mostly heard about CUDA from NVIDIA's GPU chips, because they are kind of customized CUDA is kind of customized to run on NVIDIA's GPU chips, which probably GPU chips is what has probably led to this huge this discovery of GPUs is what has led to this huge expansion in AI capabilities in the last few years. So definitely those are some of those foundational things that I think were kind of critical to know. Then we started a discussion with talking about statistical prediction and the importance of supervised learning. And during that discussion, we discussed about some of the, I believe is Derek took this chapter, I believe, and talked a lot about the some foundational concepts in machine learning. So we talked about regression, linear regression methods. We reviewed the concept of variance, supervised learning, unsupervised learning, the differences there. We talked about classification. We talked about different kinds of models and regularizations and things like that. So I think also a really great baseline to sort of have a mental model for more complex architectures that we were going to discuss later on. Then we had we talked about time series analysis. I think this was the third chapter, still in our first presentation, where we covered some of the autoregressive models. I think in the chapter there was a discussion about ARIMA, and AR in general. So this whole concept of creating mental models for sequence prediction and the basics of temporal dependencies in data. So I think that was a very profound chapter, and with lots of resources that I believe Derek shared as well afterwards. I think those were the first three chapters. Then we proceeded to the next three chapters where we discussed about some online learning and regret minimalization. And during this discussion, we essentially explored how models learn from data that's arriving sequentially, and really trying to aim at minimizing cumulative predictive error was the minimizing predictive error. Essentially, regret was what this chapter was centered on. So essentially, sequential learning where data points arrive one by one, and then focusing on minimizing a regret. So the average loss of information compared to the best fixed predictor was what we were sort of emphasized on. Then we talked about reinforcement learning. And the center here was we tried to I think we talked about we presented agents learning via rewards in the Markov decision process. So the MDPs, I think Derek talked also about Markov decision processes, MDPs, gradient-based reinforcement learning, optimizations, etc. So really laying the groundwork for alignment and fine-tuning in general. Then we discussed about the Markov model. I believe this was chapter 6, if I'm not getting those numbering wrong. And Markov models is based on this concept of assuming memoryless transition. So this whole concept that future states depends on the current state. And we talked about some of the applications in the evolutionary biology. I think we have one of us here who is a bioinformatician. So how we use Markov chain Monte Carlo in Bayesian methods in phylogenetic analysis, and how so the whole essence of predicting future states depending on the current state, essentially. So and we try to align that in the context of machine learning. So I think it sort of presents us with a good mental model for thinking about large language models and sequential dependencies. So that was it for the first, I believe, the first 6 chapters. Then afterwards, what came afterwards, we discussed a little bit. Section 2 was mostly about sequential prediction. And in sequential prediction, I think this is where Diane started with, with some of the layers, deep learning networks. Essentially, I think the different deep learning methods that are out there for sequential and language modeling. So I think we discussed a little bit about the different architectures that led to, or at least that lead to the basic transformers that we currently have. Then we talked about recurrent neural networks and recurrent neural networks. Well, but before I talk about recurrent neural networks, one of the things that was discussed was this whole concept, which I didn't really understand very much, was this whole concept of back propagation. I believe Derek shared some resources on back propagation from a presentation. Trying to find it in the Slack channel, but I think it was a really great resource which I was trying to review just prior to this. I was trying to review this prior to this lecture. So the concept of back propagation here it uses chain rule to compute gradients of the loss of function with respect to each weight in within the network, allowing us to update weights and reduce prediction error. So So this is foundational to statistical prediction within neural networks. So this idea of using layers and backpropagation to learn complex patterns from the data for things like classification and regression, etc. So not an expert in this. I think Derek might have more ideas on this example that he gave during this slide presentation, but I thought it was a very useful and practical example of backward propagation essentially. So thanks a lot for sharing those slides. And I think I saw something that you shared in it as well regarding softmax. Yeah, softmax as well, where we can have, which might be relevant when we start talking about tokenization, but this whole idea of really not getting into a point where we have a limit, we have so many tokens that we have a limit to what we can compute or put together. So I thought that was very insightful slide. So I just wanted to share that. So the link is there for those who would like to review that. So then we talked about recurrent neural networks. So these RNNs they handle sequences by maintaining internal memory across steps. So it's useful for modeling time and language data. So I think this introduced us to this concept of stateful models for sequences. So I think Diane did a really excellent job with, in trying to decomplexify a very complex topic. I would say one of those that had difficulties understanding and had to go back and review it myself. Then I think Diana took us into long short term memory and gated recurring networks. And I think this builds on the whole RNN framework. So this RNN variants sort of manage long-term dependencies using gates to better retain and forget information across different sequences. So enhancements of the recurrent neural networks helps us to manage long-term dependencies. So that's why this chapter was really relevant. Before we moved on, then afterwards we moved on to embeddings. We discussed a little bit about embeddings in general. We talked about the fact that words and tokens are mapped to vectors or embeddings to capture semantic similarity, which is foundational to modern natural language processing models. So essentially explaining or exploring how language can be represented as vectors. So this chapter was covered by David. I don't know if David is here yet, but I think he also shared a resource about Word2Vec, which I thought was quite interesting. I had a chance to play with it a little bit, but thanks for sharing that. So I think it's a great resource to see some of the practical applications of Word and embeddings. So converting words into embeddings, and this is really important because this helps to this is really one of the fundamental building blocks for large language models. So thanks to David again for doing a really excellent job on a very complicated topic as well. Then we had the discussion on encoders, essentially compressing and decompressing information. And then we talked about decoder-only transformers because most of the models that we currently have are pretty much GPT based. So we kind of discussed about some of the architecture that's associated with some of the current LLMs that we currently have. So I think Derek did a really excellent job with that chapter as well. So that was it. With a quick recap, I know we had not met for quite a few weeks due to daylight savings. I felt it would be essential to maybe say one or two words about the previous chapters and what we had covered up to this point, before proceeding on to the next chapters. So we're going to talk a little bit about tokenization, and tokenization is going to build on what we again build a little bit on what Derek had David had covered on decoder only transformers, which is really what most of our models are essentially built on. And the key questions here is how do we process, how are these models able to process text so efficiently, or how do we encode word without recurrence? So if you think about early in 2022, when ChatGPT was sort of released, made public, we had probably see a lot of hallucinations, lots of errors and things like that. But and see how much things have changed since 2022 to where we are today in terms of in terms of how text is being processed. So the whole concept of tokenization is in the most simplest terms, really chopping sentences into tiny bits, like almost like, using a I don't know if chopping, using a knife, like to chop off the text into very smaller units called tokens, which can be converted into numbers. That is a lot easier for a machine to understand, or a computer to understand. So large language models process tokens. They don't really process raw characters or full words. They try to convert those words into numerical values, and those are the values that are actually interpreted, understood by the machine, and then used by the machine. So, and there are different kinds of tokenizers that are currently being used out there. So at the beginning, we have an input. Like here, we have the example of the teacher taught the, so the word "the" has been converted. So this is a tokenizer, and then this word "the" has been converted into a token, and here the token is 342. And there are different tokens, and these words can be further broken down into even way smaller pieces. And it's these tokens that are converted into that are these numerical values that are fed into the LLMs that eventually we use. There is I think I saw there was a website. Let me see. It's called Tokenizer. Yeah, I can't recall. Let me see if I can find it somewhere. I think I had it in one of my, I just can't find it. There's a really nice website that helps to convert words into tokens. Let me see. I can find it. Yeah, this is it.
Yeah, it's in your bookmarks. It just says, yeah, you got it.
Okay, awesome. Thank you. Yeah, so this is the website. I might let me just see if I can put the link in the chat. Where's my chat? Yeah. So yeah, this website really does a great job of, let's say I love the Gen AI book club. It automatically converts the words into tokens. So each of the colors here represents a different token. Let me try to see if I can find a longer sentence from somewhere and just paste it there. Yeah, let me paste this whole paragraph here. So copy the tokenizer. Yeah, let me just paste it here. And you see that it attributes a different color to each of those tokens. So it converts each of these words into individual tokens here. So you'll see here that the word "I" is just it's a different token, and the number that has been assigned to it is the number 40. The name "love" here has been tokenized as 3047, as you can see there. Is a different token. So it breaks down these words into tokens. So this whole chunk of text that I just put in here has a total token count of 46. So different tokens that have been generated. So essentially you're chopping down sentences into different individual pieces. But again, there are different tokenizers. So here I'm using the GPT-4 for O for the for the tokenizer here, but there's just a variety of other other examples, other tokenizers that you could play with as well that's out there. These are some of the popular ones that a lot of people are using. There's the Llama one as well that I've heard a lot about, Code Llama. There, yeah, the OpenAI too has quite OpenAI models have quite a few tokenizers that I think they've put out there, which I think you can all try to play. Quen as well. Just a lot of different tools that enables converting text again, converting text or chopping down text into fundamental pieces, attributing numbers to them that can easily be interpreted by a machine or by a computer. And this is the same kind of concept or idea that's done with imaging as well. This whole idea of converting image into its most tiny pieces. So again, generative AI, even with imaging, for example, as we were discussing earlier, first essentially the same fundamental concepts. So that's what I just wanted to describe with this particular slide. This whole process, how large language models is able to convert it's essentially text into numerical vectors that can be fed into an LLM in that sense. Then we have different kinds or different methods or different kinds of approaches for tokenization. So we have the character level um, tokenization approach where each character is essentially a word. And some of the advantages here is that it's simple, it can handle all inputs. The cons is that it can be inefficient, especially for long sentences. Yeah, and yeah, long sentences. And you can also get to a point where you have just so many tokens that is just so difficult to put it all together. So that's why I love this concept that again, Derek, really appreciate you for making those slides and making that available. I kind of was kind of laying the foundation for understanding the whole concept of softmax, where you begin to have a limit to how many tokens can be generated, because you can't have an infinite. Some of these large language models have trillions and trillions. Have been trained on trillions and trillions of tokens and very huge data sets. But you want to kind of figure out a way to structure all those tokens within the training data set, so it's a little bit more efficient and more useful for the models. There's also word level tokenization tokens, where each word is essentially a token. We have um we have some pros to that. It's intuitive. You can have shorter sentences, but the problem is you would have fixed vocabulary, some unseen words, some uh um you can have fixed vocabulary that would lead to some unseen words and misspellings. And that's why we see the struggle with large language models with different languages, struggling with different languages, or struggling with some of the challenges that I essentially laid out at the beginning of the of this discussion, why the large language models struggle with strings, reversing strings, and things like that. So these are other examples in the image below. These are other methods that are used for tokenization. We have the n-gram, which uses continuous sequences in n terms as tokens and captures the continuity within the text. So we have an example here: artificial intelligence will, etc., etc., etc. We have character, which I just described already, where you can pretty much break down each character as independent tokens, which can allow for more granular analysis. I already talked about word tokenizations, where it just essentially breaks down the word into different pieces, and it's just a lot easier to process. Talked about then there's Morphem as well, which uses the smallest meaningful units of language as tokens, and this is ideal for inflected languages. So and again, these are some examples of tokenizations from this particular method. Then we have subwords. Subwords really splits words into commonly occurring combinations or parts using a method called BPE. I think we're going to discuss about that later on. So you have a word like art, artificial, etc., etc. So essentially kind of converting words into combinations that are a little bit more frequent. So I think I might have a practical example later on. So subword tokenization was what I was trying to describe here, where you can split a word into subword units, like playing can be converted into play plus play, with the hashtag and ing. And it uses an algorithm called bit pair encoding, or BPE, that starts with character level tokens and iteratively merges frequent pairs. So you essentially start with a common word and then try to predict the next letter, or the next or the next word. Essentially, there is a video on Kapati's channel on that as well, which I would encourage also to have a chance to review. But the whole idea behind bit pair encoding, or BPE, is it starts with a character. It starts with a character, um, and frequent. Then you count frequent pairs or merge pairs, and then you sort of repeat the process. I think I had an example. Yes, here. Yeah. So you start with a set of characters, and then you count the frequent pairs, you merge the pairs, and you sort of iterate or repeat that process. And an example here would be, if we had the word text, the text here, as our input, we have low, lower, lowest. So what happens with BPE is it essentially breaks down the word into individual it's individual characters with spaces in between. So here we have L, we have a space, we have O, we have a space, etc., etc. So when you begin the merging process that I was sort of referring here, is first of all you count the frequent pairs. So here we can see that in each of these words, the word L, O, and W um, um, appear very frequent. They're kind of almost common for all the three words in this particular example. So we can choose to have LO as one of the tokens, as you see here. So you sort of count the frequent pairs within the word, and and then you can append the next word there. You see that the next word W is common to all, but after you have the word low, you can try to merge. Now this can form one token, and then you can try to form the next most common word. So and the next most common character here, in this case, in lower and lowest, we would have E. So you can combine E and the low to form lowy, and this lowy can be another character. So the final vocabulary would look like something like this, where we have low, because low, LOW, is the most frequent word in this initial breakdown. And then we have lower, which is the second most common, because we have lower in LOWE, and then we have that also appearing within lowest. Then we can just append these other characters there, like RST. So that's the foundational idea behind behind BPEs, so bit pair encoding. And one of the advantages to it, according to the book that we are reviewing, is just the efficiency that it comes with, the efficiency, the generalizations capabilities there, and I already gave you the example with the word low and lower, and how you can form different words there as well. So this is very useful for especially in handling very rare words that we don't words that we don't see very frequently, but also tokenizations in general with most of our large language models. So yes, so that's it about that. So why subword tokenization? So it covers, like I said, it covers unseen words. It reduces frequency, length, and character level, and it's used in most of the modern LLMs that we have today. Yeah, so that's pretty much it for tokenization. I think the central message with this chapter, um the central message of this chapter on tokenization is really to understand the whole frame of large language, the building blocks, the idea that words are broken, the idea that tokenization enables text, most of the text that we have in the in the training data to be chopped into its most fundamental fragments or pieces, and then converting those pieces into numerical vectors or numbers that are easily interpretable by machine. So that's the whole idea of tokenization. And now there are just too many methods. There are different ways in which people are doing this. There are just a myriad of applications and tools out there to help with tokenizations in general. So yeah, so that's the general framework behind behind tokenization. So we're going to move to positioning.
Brian,
Yes.
while we're here, could you elaborate a little bit more how tokenization might be different for languages beyond English, and also how it might affect you in your biology studies?
Yeah, and yeah, thanks a lot. Really a great question. I'll start with the last part with my in especially in biology and applications in medicine. In medicine in particular, because my background my background is in medicine. I'm a physician and epidemiologist, and the challenge in diagnostics in general is we have a lot of cases, or we can have a clinical case with just information about a patient in text file, but the one of the biggest challenges that all the current large language models have is this multimodal integration. This multimodal integration essentially combining text information from a case to information that might be present about that case in a different mode of in a different format. For example, a chest X-ray, an EKG, a CT scan, or even a histopathological slide for something, for cancer or something. I don't know. The biggest challenge that current models have, this is not unique to any of them. I think all of them are struggling with this. Is how do you combine text tokenization with with imaging, like embeddings within images. So I think they kind of struggled there. But I think the biggest challenge here is the way weightings are done with text tokens is a little bit different from the way weightings are done with the embeddings that we have in imaging. So there's some sort of a disconnect that's occurring there. So in applications in biology, in medicine in general, I think we are not at the we are not there yet. I think we are still really struggling on how to connect the dots with just multimodal integration. And there's a lot of research groups that are doing research on how to fine tune that process. I do have a few papers from some groups from Stanford University that have done work in research in that direction in order to sort of streamline that process. But it's a great question. I think it's probably one of the biggest technical challenge in AI that we will have to face moving forward. Um, and Yeah, I do think so. And I see that we do have a chapter on multimodal integration towards the end. So it'd be great if we cover that chapter as well. But regarding the first question, how do we deal with rare words? I think that was a question. Yeah. The advantage of BPEs is this I think it makes it a little bit easy for us to handle words could be a little bit rarer. And I think in the website, the Tick Tokenizer website that I shared, there are some specific tokenizers there that are adapted for much rarer words, foreign languages, which I think current large language models sort of struggle with. So Yeah, so I think the people who are developing new methods, new approaches, and I think I laid out a few examples or some common examples of tokenizers that is out there. But I think there's a lot of innovation happening in that space, and people are computing new methods on how to handle different kinds of um data sources. Obviously, English is very popular, it's very common, and it might be more difficult to have, a customized large language model in maybe a rarer language that's not commonly spoken. How do you do that, and how do you prevent hallucinations from or reduce error in those kinds of models? So my sense is it's um I think the researchers in AI are pretty much beginning to understand this a little bit more and kind of trying to uncover new ways or new approaches to dealing with how do you deal when you have limited resources or limited training data or training resources, especially on a rare language or and things like that, or rare words and things like that, things that are not commonly used, and how do you adjust the weightings for that? But thanks a lot for asking that as well. Um, any other question before I proceed to the chapter on positional encoding? Okay, great. I have to render this in my R Studio because it has to take its time. And okay, good. I think that's working. Then I can try to share this. Are my slides visible?
Yes, yes, they are.
Thanks a lot. Yeah, so the next chapter we're going to have to briefly discuss about here is positional encodings. And please feel free to help me here because this was one of my most difficult it kind of a little bit positional encodings as well. The challenge that most so transformers lack recurrence, and I think we discussed a little bit about recurrent neural networks, and I think Diana touched a little bit on this when we discussed about on this subject later on, and how do you fix that? So positional encoding, it becomes especially useful because there's no inherent sense of word order. Large language models are not able to contextualize that. So the solution there is to add some positional information to token embeddings, or at least within the vector. So you can have a word here like I am a robot, and you can index each of those words there, or at least each of those characters, word or characters into a specific position, and that would be, so here the word I would be 0, and it be attributed the position 0, 0, etc., etc. So you can have essentially have a matrix that have an infinite number of encodings essentially. So the way this works against another image we have that describes this whole position. So essentially, you're trying to put some order in the sentencing structures within the within 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 the text, essentially. So you're attributing some positions to different words or text that might appear in the text. So in the word, the quick brown fox over the lazy dog, you have different positions there. The position 0, position 1. So the quick fox here, you can see has been assigned. I'm not a mathematician, so bear with me with all the sign and clocks operations there. But essentially, you're converting each of those into different fragments and assigning different positions to each of those to each of those fragments. So in the book that we had initially discussed, in the not the book, the paper we had previously discussed, I think we've discussed about this before, is attention is all you need. That the paper that essentially introduced us into this whole concept of transformers, and that really revolutionized how natural language processing, natural language processing that enabled us to handle long range sort of dependencies through different attention mechanisms. So I think discuss about the different models like GPT and BERT that are essentially using this sort of infrastructure architecture to build on for better processing of text. So this is the basic anatomy of a transformer architecture. I think there is a similar image in Kapathi's video on, I think he has a video on how large language models work on his YouTube channel, which I would encourage you all to go revisit. But essentially, we have an input that, an input embedding inputs and input embeddings that's converted through positional encoding. We have multi-head attention and at norm, we have a feed forward model, etc. And all of that is fed into this multi-head attention. You have an at and norm there as well. So yeah, so essentially building on each of those steps or methods in order to build the output probabilities for a specific input. So positional encoding addresses this challenge by injecting positional information into the input embeddings, and this allows transformers to effectively process sequences by identifying the sequential order of the tokens. So the naive approaches, we have one-hot encoding, which essentially takes a unique vector per position. But the issue here is it's difficult to apply scaling law. I think we're going to talk about scaling laws. Is it next time or maybe the week after? And then no ordinality as well. Then we have linear indexes, but the issue there as well is the challenge with large values and just poor generalization. So what we really need here is the need for, we have a need for unique bounded and relative aware encodings that can be used more broadly or more widely. And this concept of has been outlined in the book by the paper called Attention to Detail, that essentially laid out the foundation. I'll try to open the link here. That essentially laid down the foundation for for how GPTs, or at least transformers, are built. So really great paper that was put out really by an amazing group. And again, you will find that image here on the basic architecture or the basic anatomy of what a transformer really looks like, etc. Again, the whole concept of softmax, because you really have to, can't keep just tokenizing. You have to apply some sort of a limit to how many words. You can't have just have an infinite number of tokens and no control. So this whole concept of mathematically applying a limit to how many tokens can be generated from a particular text. So again, great work there. So the whole concept of attention is pretty much fundamental to this as well. So how it works, we have sine and cosine pairs at varying frequencies. We have wavelengths that vary from 2 to 2. We have properties unique per position. We have consistent distances. We have generalizations for longer sequences. Then we have to imagine a 512 DIM encoding for 100 token sequences. There are some additional resources in the book chapter on that as well, which I would encourage all the blog post by Marin Serhi, that I would encourage us all to if you have a chance later on to visit this on the website, where he tries to describe essentially provides us a good introduction into positional encoding within transformer models as well. So lots of other additional resources. So this is certainly not an exhaustive presentation on positional encodings, but I think it sort of lays the foundation, or at least the groundwork, for us to think about how the models that we currently have, especially the decoder only models, how they are able to take an input and generate the kind of outputs that we see. So I think in the next lecture we will discuss about the next chapter. We'll discuss about pre-training recipes. We'll talk about and the others. So we're going to probably spend some time in this chapter, essentially laying the understanding the basic foundation of modern language models. So with that, I think I'll end there. Derek, thanks a lot. It's really been a pleasure learning from you all. Thanks for dedicating so much of your time and energy into helping us all understand large language models. Yeah, the technical